नमस्कार नमस्कार Newton's laws of motion. Newton's law of motion are three basic laws of classical mechanics that describe the relationship between the motion of an object and the forces acting on it. These laws can be paraphrased as follows. Law 1. A body remains at rest or in motion at a constant speed in a straight line unless acted upon by a force. Law 1. A body remains at rest or in motion at a constant speed in a straight line unless acted upon by a force. Law 2. When a body is acted upon by a force, the time rate of change of its momentum equals the force. Law 2. When a body is acted upon by a force, the time rate of change of its momentum equals the force. Law 3. If two bodies exert forces on each other, these forces have the same magnitude but opposite directions. Law 3. If two bodies exert forces on each other, these two forces have the same magnitude but opposite directions. The three laws of motion were first stated by Isaac Newton in his Philosophiae Naturalis Principia Mathematica, the Mathematical Principles of Natural Philosophy, originally published in 1687. Newton used them to investigate and explain the motion of many physical objects and systems, which laid the foundation for classical mechanics. In in the time since Newton, the conceptual content of classical physics has been reformulated in alternative ways involving different mathematical approaches that have yielded insights which were obscured in the original Newtonian formulation. Limitations to Newton's law which have also been discovered. New theories are necessary when objects are very fast, special relativity, very massive general relativity, or very small quantum mechanics. Laws. Newton's laws are often stated in terms of point or particle masses, that is, bodies whose volume is negligible. This is a reasonable approximation for real bodies when the motion of internal parts can be neglected, and when the separation between bodies is much larger than the size of each. For instance, the Earth and the Sun can both be approximated as point-like when considering the orbit of the former around the latter, but the Earth is not point-like when considering activities on its surface. The mathematical description of motion or kinematics is based on the idea of specifying positions using numerical coordinates. Movement is represented by these numbers changing over time. A body's trajectory is represented by a function that assigns to each value of a time variable the values of all the position coordinates. The simplest case is one-dimensional, that is, when a body is constrained to move only along a straight line. Its position then can be given by a single number indicating where it is relative to some chosen reference point. For example, a body might be free to slide along a track that runs left to right, and so its location can be specified by its distance from a convenient point, 0 point, or origin when negative numbers indicating positions to the left and positive numbers indicating positions to the right. If the body's location as a function of time is st, then its average velocity over the time interval from t0 to t1 is delta s upon delta t equals to st1 dash st1 minus st0 by st1 minus st0, no sorry, by t1 minus t0. Here the Greek letter delta is used per tradition to mean change in a positive average velocity, means that the position coordinate s increases over the interval in question. A negative average velocity indicates a net decrease over that interval, and an average velocity of 0 means that the body ends the time interval in the same place as its began. Calculus gives the means to define an instantaneous velocity, a measure of a body's speed and direction of movement at a single moment of time rather than over an interval. One notation for the instantaneous velocity is to replace delta with the symbol d. For example, v equals to ds by dt. This denotes that the instantaneous velocity is the derivative of the position with respect to time. It can roughly be thought of as the ratio between an infinitesimally small change in position ds to the infinitesimally small time interval dt over which it occurs. More carefully, the velocity and all other derivatives can be defined using the concept of a limit. A function ft has a limit of L at a given input value t0 if the difference between f and L can be made arbitrarily small by choosing an input sufficiently close to t0. One writes limit t to t0 ft equals to L. Instantaneous velocity can be defined as the limit of the average velocity as the time interval shrinks to 0. ds by dt equals to limit delta t tends to 0 st plus s bracket t plus delta t minus st by delta t. Acceleration is to sorry acceleration is to velocity as acceleration is to velocity as velocity is to position. It is the derivative of the velocity with respect to time. Acceleration can be likewise be defined as a limit a equals to dv by dt equals to limit delta t tends to 0 v bracket t plus delta t dash vt by delta t. Consequently, the acceleration is the second derivative of position, often written d square L into s by d into t square. Position, when thought of as a displacement from an origin point, is a vector, a quantity with both magnitude and direction. Velocity and acceleration are vector quantities as well. The mathematical tools of vector algebra provide the means to describe motion in two, three, or more dimensions. Vectors are often denoted with an arrow as or arrow over as or in bold typeface such as. Often vectors are represented visually as arrows, with the direction of the vector being the direction of the arrow and the magnitude of the vector indicated by the length of the arrow. Numerically, a vector can be represented as a list. For example, a body's velocity vector might be v arrow v sorry arrow over v equals to within bracket 3 into mys dash sorry call sorry comma 4 into m by s, indicating that it vector bracket close, indicating that it is moving at 3 meters per second along the horizontal axis and 4 meters per second along the vertical axis. The same motion described in a different coordinate system will be represented by different numbers, and vector algebra can be used to translate between these alternatives. The physics concept of force makes quantitative the everyday idea of a push or a pull. Forces in Newtonian mechanics are often due to strength and of friction, muscle effort, gravity, and so forth, like displacement, velocity, and acceleration. Force is a vector quantity. First, translated from the Latin Newton's first law, reads: every body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces pressed upon it. Newton's first law expresses the principle of inertia. The natural behavior of a body is to move in a straight line at constant speed in the absence of outside influences. A body's motion preserves the status quo. The modern understanding of Newton's first law is that no inertial observer is privileged over any other. The concept of an inertial observer makes quantitative the everyday idea of feeling no effects of motion. For example, a person standing on the ground watching a train go past is an inertial observer, or can be idealized as one to a good approximation for many practical purposes. If the sorry, if the sorry, if the observer sorry, if the observer sorry, if the observer on the ground sees the train moving smoothly in a straight line at a constant speed, then a passenger sitting on the train will also be an initial observer. The train passenger feels no motion. The principle expressed by Newton's first law is that there is no way to say which inertial observer is really moving and which is really standing still. One observer's state of rest is another observer's state of uniform motion in a straight line, and no experiment can deem either point of view to be correct or incorrect. There is no absolute standard of rest. Second, the change of motion of the change of motion of an object is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. The change of motion of an object is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. By motion, Newton meant the quantity now called momentum, which depends upon the amount of matter contained in a body, the speed at which that body is moving, and the direction in which it is moving. In modern notation, the momentum of the object of a body is the product of its mass and its velocity. A over p equals to m into v over a over v. Newton's second law in modern form states that the time derivative of the momentum is the force F. A over F equals to d into a over p by dt. If the mass m does not change sorry if the mass m does not change with time, then the derivative acts only upon the velocity, and so the force equals the product of the mass and the time derivative of the velocity, which is the acceleration. A over f equals to m into a over a, as the acceleration is the second derivative of position with respect to time. This can also be written a over f equals to m into d square by dt square into rho s. The force the force acting on the force acting on a body acts as vectors, and so the total force on a body depends upon both the magnitudes and the directions of the individual forces. When the net force on a body is equal to zero, then by Newton's second law the body does not accelerate and it is said to be in mechanical equilibrium. A state of mechanical equilibrium is stable if when the position of the body is changed slightly, the body remains near that equilibrium, otherwise the equilibrium is unstable. A common visual representation of forces acting in concert with the free body diagram, which systematically portrays a body of interest and the forces applied to it by outside influences. For example, a free body diagram of a block sitting upon an inclined plane can illustrate the combination of gravitational force, normal force, friction, and string tension. Newton's second law is sometimes presented as definition of force, that is, a force is that which exists when an inertial observer sees a body accelerating. In order for this to be more than a tautology, acceleration implies force, force implies acceleration. Some other statement about force must also be made. For example, an equation detailing the force might be specified like Newton's law of universal gravitation by inserting such an expression for F a over F into Newton's second law. An equation with predictive power can be written. Newton's second law has also been regarded as setting out a research program for physics, enabling establishing that important goals of the subject are to identify the forces present in nature and to catalog the constituents of matter. Third, to every action, there is always opposed and equal reaction, or the mutual actions of two bodies depend the bodies upon each other are always equal and directed to contrary parts. To every action, there is always opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. Every overly brief paraphrases of the third law like action equals reaction have contributed to an problem that has already been devised generations of students. The action and reaction apply to different bodies. For example, consider a book at rest upon a table. The Earth's gravity pulls down upon the book. The reaction to that action is not the support force from the table holding up the book, but the gravitational pull of the book acting on the earth. The modern view is that Newton's third law is a consequence of a more fundamental principle, the conservation of momentum. The latter remains true even in cases where Newton's statement does not. For instance, when force fields as well as material bodies carry momentum, and when momentum is defined properly in quantum mechanics as well in Newtonian mechanics, if two bodies have momentum, A over P1 equals to A over P2. Sorry, A, A over P1 and A over P2 respectively, then the total momentum of the pair is A over P equals to A over P1 plus A over P2, and the rate of change of A over P is d into A over P by dt equals to d into A over P1 by dt plus A over d into A over P2 by dt by Newton's second law. The first term is the total force upon the body on the first body, and the second term is the total force upon the second body. If the two bodies are isolated from outside influences, the only force upon the first body can be that from the second, and vice versa. By Newton's third law, these forces have equal magnitude but opposite directions, so they cancel when added, and A over P is constant. Alternatively, if A over P is known to be constant, it follows that the forces have equal magnitude and opposite direction. Candidates for additional laws. Various sources have proposed elevating other ideas used in classical mechanics to the status of Newton's law. For example, in Newtonian mechanics, the total mass of a body made by bringing together two smaller bodies in the sum of their individual masses. Frank Wilczek has suggested calling attention to this assumption by designating it Newton's zeroth law. Another candidate for a zeroth law is the fact that that at any instant a body reacts to the forces applied to it at that instant. Likewise, the idea that forces act like vectors, or in other words, obey the superposition principle, and the idea that forces change the energy of a body when described as fourth law. Work and energy physicists developed the concept of energy after Newton's time, but it has become an inseparable part of what is considered Newtonian physics. Energy can broadly be classified into kinetic due to a body's motion and potential due to a body's position or relative to others. Thermal energy, the energy retained by heat flow, is a type of kinetic energy not associated with the macroscopic motion of objects, but instead with the movements of the atoms and molecules of which they are made. According to the work energy theorem, when a force acts upon a body while that body moves along the line of the force does not work upon the body, and the amount of work done is equal to the change in the body's kinetic energy. In many cases of interest, the net work done by a force when a body moves in a closed loop, starting at a point, moving along some trajectory, and returning to the initial point, is zero. If this is the case, then the force can be written in terms of the gradient of a function called a scalar potential, over f equals to minus a over delta into u. This is true for many forces, including that of gravity, but not for friction. Did almost any problem in a mechanics textbook that does not involve friction can be expressed in this way, and the fact that the force can be written in this way can be understood from the conservation of energy. Without friction to dissipate a body's energy into heat, the body's dissipated body's energy into heat. The body's energy will trade between potential and non-thermal kinetic forms, while the total amount remains constant. Any gain of kinetic energy which occurs when the net force on the body accelerates it to a higher speed must be accompanied by a loss of potential energy. So the net force upon the body is determined by manner in which the potential energy decreases. Examples: in uniformly accelerated motion, if a body falls from rest near the surface of the earth, then in the absence of a resistance, it will accelerate at a constant rate. This is known as free fall. The speed retained during free fall is proportional to elapsed time, and the distance traveled is proportional to the square of the elapsed time. Importantly, the acceleration is the same for all bodies independently of their mass. This follows from combining Newton's second law of motion with his law of universal gravitation. The latter states that the magnitude of the gravitational force from the earth on the body is F equals to G, capital G into capital M into small m by r, small r square, where m small m is the mass of the falling body, capital M is the mass of the earth, capital G is Newton's constant, and small r is the distance from the center of the earth to the body's location, which is very nearly the radius of the earth. Setting this equal to small m into small a, and the body's mass small m cancels from both sides of the equation, leaving an acceleration that depends upon capital G and capital M, and r small r can be taken to be constant. This particular value of acceleration is typically denoted small g equals to capital G into capital M by r square. 9.8 into meter per second square. The body is not really meter, 20 meter by second square. 9 g equal 9.8 slow down by a small, 9.8 into meter by second square if the body is not released from rest but instead launched upward and slash or horizontally with non-zero velocity, then free fall becomes projectile motion. When air resistance can be neglected, projectiles follow parabola-shaped trajectories because gravity affects the body's vertical motion and not its horizontal. At the peak of the projectile's trajectory, its vertical velocity is zero, but its acceleration is g downwards, and it is at all times setting the wrong vector equal to zero. A common confusion among physics students. Uniform circular motion. When a body is in uniform circular motion, the force on it changes the direction of its motion but not its speed. For a body moving in a circle of radius r at a constant speed, v its acceleration as v equals to v squared by r. When it is directed toward the center of the circle, the force required to sustain this acceleration, called the centripetal force, is therefore also directed toward the center of the circle has magnitude and into v squared by r. Many orbits, such as that of the moon around the earth, can be approximated by uniform circular motion. In such cases, the centripetal force is gravity, and by Newton's law of universal gravitation has magnitude capital G into capital M into small r by small r squared, where m capital M is the mass of the larger body being orbited. Therefore, the mass of a body can be calculated from observations of another body orbiting around it. Newton's cannonball is a Newton's cannonball is a thought experiment that interpolates between a projectile motion and uniform circular motion. A cannonball that is knocked quickly off the edge of a tall cliff will hit the ground in the same amount of time as if it were dropped from rest, because the force of gravity only affects the cannonball's momentum in the downward direction, and its effect is not diminished by horizontal movement. If the cannonball is launched with greater initial horizontal velocity, then it will travel farther before it hits the ground, but it will still hit the ground in the same amount of time. However, if the cannonball is launched with an even larger initial velocity, then the curvature of the earth becomes significant. The ground itself will curve away from the falling cannonball. A very fast cannonball will fall away from the inertial straight line trajectory at the same rate that the earth curves away beneath it. In other words, it will be in orbit, imagining that it is not slowed by a resistance or obstacles. Harmonic motion. Consider a body of mass and able to move around the x-axis, and suppose an equilibrium point exists at the position x equals to 0, that is, at x equals to 0, the net force upon the body is the zero vector, and by Newton's second law, the body will not accelerate if the force upon the body is proportional to the displacement from the equilibrium point and directed to the equilibrium point. Then the body will perform simple harmonic motion, writing the force as F equals to minus K into R. Newton's second law becomes M into D square into X by D2 square equals to minus KR. This differential equation has the solution xt equals to A cos Wt plus B cosine Wt, where the frequency W is equal to under, sorry, under root sorry under root k by m, and the constants a and b can be calculated knowing for example the position and velocity of the body as at a given time like t equals to 0. One reason that the harmonic oscillator is a conceptually important example in that it is good approximation for many systems near a stable equilibrium, stable mechanical equilibrium. For example, a pendulum has a stable equilibrium in the vertical position. If motionless there, it will remain there, and if pushed slightly, it will swing back and forth, neglecting air resistance and friction in the pivot. The force on the pendulum is gravity, and Newton's second law becomes d squared into theta by d2 square equals to minus g by l into sine theta, where l is the length of the pendulum and theta is its angle from the vertical. When the angle theta is small, the sine of theta is nearly equal to theta's Taylor series, and so this expression simplifies to the equation of a simple harmonic oscillator with frequency w equals to under g by l. A harmonic oscillator can be damped often by friction or viscous drag, in which case energy leaks out of the oscillator and the amplitude of the oscillations decreases over time. Also, a harmonic oscillator can be driven by an applied force, which can lead to the phenomenon of resonance. Objects with variable mass. Newtonian physics treats matter as being neither created nor destroyed. Though it may be rearranged, it can be the case that an object of interest gains or loses mass because matter is added to or removed from it. In such a situation, Newton's law can be applied to the individual pieces of matter, keeping track of which pieces belong to the object of interest over time. For instance, if a rocket of mass and entity moving at a velocity vector continue to t sorry arrow over arrow over v into t ejects matter at a velocity arrow over u relate to the rocket, then arrow over f equals to m into d into arrow over v by dt minus arrow over u into dm by dt, where arrow over f is the net force, external force, example a planet's gravitational pull. Rigid body motion and rotation. A rigid body is an object whose size is too large to neglect and a rigid body is an object whose size is too large to neglect and which maintains the same shape over time. In Newtonian mechanics, the motion of a rigid body is often understood by separating it into movement of the body's center of mass and movement around the center of mass. Significant aspects of the motion of an extended body can be understood by imagining the mass of that body concentrated to a single point known as the center of mass. The location of the body's center of mass depends upon how that body's material is distributed. For a collection of point-like objects with masses m1 and at position arrow r1 arrow r, and the mass of center of mass is located at arrow r equals to sorry arrow r equals to summation and arrow r equals to summation over n sorry arrow r equals to arrow r equals to summation under n I equals to 1 into mi into rho over ri by m, where m is the total mass of where m is where m is the total mass of the collection in the sense of a net external force. The center of mass moves at a constant speed in a straight line. This applies, for example, to a operation between two bodies if the total external force is not zero and the center of mass changes velocity as though it were a point body of mass, and this follows from the fact that the internal force within the collection, the forces that the objects exert upon each other occur in balanced pairs by Newton's third law. In a system of two bodies with one much more massive than the other, the center of mass will approximately coincide with the location of the more massive body. Relation to other sorry Relation to other formulations of classical physics, classical mechanics can be mathematically formulated in multiple different ways other than Newtonian descriptions, which itself, of course, incorporates contributions from others both before and after Newton. The physical content of these different formulations is the same as the Newtonian, but they provide different insights and facilitate different types of calculations. For example, Lagrangian mechanics helps make apparent the connection between the metrics and observation laws, and it is useful when evaluating the motion of constant bodies like a mass restricted to move along a curving track or on the surface of a sphere. Hamiltonian mechanics is convenient for statistical physics, leads to further insight about symmetry, and can be developed into sophisticated techniques for perturbation theory. Due to the breadth of these topics, the discussion here will be confined to concise statements of how they reformulate Newton's law of motion. Lagrangian mechanics differs from the Newtonian formulation by considering entire trajectories at once rather than predicting a body's motion at a single instant. It is traditional in Lagrangian mechanics to denote position with q and the velocity with q q dot over q. The simplest example is the simplest example is a massive point article, the Lagrangian, for which can be written as difference between its kinetic and potential energies L into bracket q dash dot over q bracket close equals to t minus q, where the kinetic energy is t equals to 1 by 2 m into m into dot over z over q square, and the potential energy is the function of the position v into under bracket q physical path that can the particle will take the the physical part that the particle will take it between initial point qi and the final point qf is the path for which the integral of Lagrangian is stationary. Hamiltonian In Hamiltonian mechanics, the dynamics of a systems are represented by a function called the Hamiltonian, which in many cases of interest is equal to the total energy of the system. The Hamiltonian is a function of the positions and the mass of all the bodies making up the system. It may also depend explicitly upon time. The time derivatives of the position and momentum variables are given by external by partial derivatives of the Hamiltonian by Hamiltonian's equations. The simplest example is a point mass and constraint to move in a straight line under the effect of a potential acting Q for the position, the coordinate, and P for the body's momentum. Hamiltonian H and sorry, when acting Q for the position, coordinate, and P for the body's momentum. Hamilton-Jacobi. The Hamiltonian-Jacobi equation provides yet another information of classical mechanics, one which makes it for mathematically analogous to wave optics. This formulation also uses Hamiltonian functions, but in a different way than the formulation described above. The paths taken by bodies or collections of bodies are deduced from a function as in bracket A over given comma I over q2 dot comma q2 dot t bracket close of position over qi and time t in relation to other physical theories, thermodynamics and statistical physics. In statistical physics, the kinetical theory of gases applies Newton's law of motion to large numbers, typically on the order of Avogadro's number of particles. Kinetic theorem can explain, for example, the pressure that a gas exerts upon the container holding it and the aggregate of many impacts of atoms, each imparting a tiny amount of momentum. Electromagnetism. Newton's three laws can be applied to phenomena involving electricity and magnetism, though subtleties and caveats exist. Coulomb, Coulomb's law for the electrical force between two stationary electrically charged bodies have much the same mathematical form as Newton's law of universal gravitation. The force is proportional to the product of charge and inversely proportional to the square of the distance between them and the diagonal along the straight line between them. Special relativity. In special relativity, the rule that Jack called Newton's zeroth law breaks down the mass density terms. The two object is not merely the sum of the mass of the individual pieces. Newton's first law inertial motion remains true in the form of Newton's second law that force is the rate of change of momentum also holds as does the observation of momentum. General relativity is the theory of relativity that advances beyond that of Newton. In general relativity, gravitational force is imagined as gravity of spacetime, a curved path like a orbit is not the result of a force deflecting the body from an ideal straight line path, but rather than bodies attempt to fall freely through a background that is itself curved by the presence of other masses. It is marked by John Archibald Wheeler that has become proverbial among physicists, summarizing the theory space-time tells matter how to move, matter tells space-time how to curve. Miller himself thought of this reciprocal relationship as a more generalized form of Newton's third law. The relation between the mass distribution and space-time curvature is given by the Einstein field equations, which require tensor calculus to express quantum mechanics. Quantum mechanics is a theory of physics primarily developed to understand microscopic phenomena, behavior at the scale of molecules, atoms, and subatomic particles generally, and usually speaking, the smaller a system is, the more inadequate mathematical model will require understanding quantum effects. The conceptual underpinning of quantum physics is very different from that of classical physics. Instead of thinking about quantities like position, momentum, and energy as properties that an object has, one considers what result might appear when a measurement of a chosen type is performed. History concepts invoked in Newton's law of motion, mass, velocity, momentum, force have predecessors in earlier work. The content of Newton's physics was further developed after Newton's time. Newton combined knowledge of celestial motions with the study of events on Earth and showed that one theory of mechanics could encompass both antiquity and medieval background. Subject of physics is often traced back to Aristotle. However, the history of the concepts involved is obscured by multiple factors, and exact correspondence between Aristotelian and modern concepts is not simple to establish. Aristotle did not clearly distinguish what we would call speed and force, and he used the same term for density and viscosity. He conceived of motion as always through a medium rather than through space. In addition, some concepts often termed Aristotelian might later be contributed to his followers and commentators upon him. These commentators found that Aristotelian physics has difficulty explaining projectile motion. Aristotle divided motion into two types: natural and violent. The natural motion of terrestrial solid matters was to fall downwards, and whereas a violent motion could push a body sideways. Moreover, in Aristotelian physics, a violent motion requires an immediate cause separated from the cause of its violent motion. The body would revert to its natural behavior, yet a javelin continues moving after it leaves the hand of its thrower. Aristotle concluded that the air around the javelin must be imparted with the ability to move the javelin forward. John Philoponus, a Byzantine Greek thinker active during the sixth century, found this absurd. The same medium, air, was somehow responsible both for standing motion and for impending it. If Aristotle's idea was to Philoponus said our bees would launch weapons by blowing upon them with willows. Philoponus argued that setting a body into motion imparted a equally impetus that could be contained within the body itself as long as its impetus was sustained, the body would continue to move. In the following centuries, versions of impetus theory was advanced by individuals including Ed-Din al-Bitroji, Avicenna, Abu al-Barakat al-Baghdadi, John Buridan, and Albert of Saxony. In retrospect, the idea of impetus can be seen as a forerunner of the modern concept of momentum, the intuition that objects move according to some kind of impetus persists in many students of introductory physics. Inertia and the first law. The modern concept of inertia is credited to Galileo based on his experiments. Galileo concluded that the natural behavior of a moving body was to keep moving until something else interfered with it. Galileo recognized that in projectile motion the Earth's gravity affects vertical but not horizontal motion. However, Galileo's idea of inertia was not exactly the one that would become codified into Newton's first law. Galileo thought that a body moving a long distance inertially would follow the curve of the Earth. This idea was corrected by Isaac Beeckman, René Descartes, and Pierre Gassendi, who recognized that the inertial motion should be motion in a straight line, force, and the second law. Christian Huygens and Horologium Oscillatorium 1673 put forth the hypothesis that by the action of gravity, whatever its sources, it happens that bodies are moved by emotions composed both of a uniform motion in one direction or another and of a motion conformal due to gravity. Newton's second law generalized this hypothesis from gravity to all forces. One important characteristic of Newtonian physics is that forces can act at a distance without requiring physical contact. For example, the Sun and the Earth pull on each other gravitationally despite being separated by millions of kilometers. This constraint contracts with the idea championed by Descartes, among others, that the Sun's gravity held planets in orbit by swirling them in a vortex of transparent matter. As ether, Newton considered ethereal concentration of force but ultimately rejected them. The study of magnetism by William Gilbert and others created a precedent for thinking of material forces and unable to find a quantitatively satisfactory explanation of this law of gravity in terms of an ethereal model. Newton's eventually integrated Fino hypothesis, whether or not a modern model like Descartes' vortices could be found to underline the Principia's theorem of motion and gravity. The first grounds for judging them must be the successful predictions they made, and indeed, since Newton's time, every attempt at such a model has failed. Momentum conservation and the third law. Johannes Kepler suggested that gravitational attractions were reciprocal, that for example the moon pulls on the earth while the earth pulls on the moon, but he did not argue that such pairs are equal and not opposite. In his Principles of Philosophy 1644, Descartes introduced the idea that during a collision between bodies, a quantity of motion remains unchanged. Descartes defined this quantity some, somewhat imprecisely by adding up the products of the speed and size of each body, where size for him incorporated both volume and surface area. Moreover, Descartes thought of the universe as a plenum that is filled with matter, so all motion required a body to displace a medium as it moved. During the 1650s, Huygens studied collisions between Earth spheres and reduced principle that is now identified as the conservation of momentum. Christopher Wren would later deduce the same rules for elastic collisions that Huygens had, and John Wallis would apply momentum conservation to study inelastic collisions. Newton cited the work of Huygens, Wren, and Wallis to support the validity of this third law. Newton arrived at his set of three laws incrementally in his 1684 manuscript written to Huygens. So he listed four laws: the principle of inertia, the change of motion by force, a statement about relative motion that would today be called Galilean invariance, and the rule that interactions between bodies do not change the motion of their center of mass. In later manuscript, in later manuscript, in a later manuscript, Newton added a law of motion and reaction by saying that this law and the law regarding the center of mass implied one another. Newton probably settled on the representation or settled on the presentation in the Principia with three primary laws and then other statements reduced to corollaries during 1685 after the Principia. Newton expressed his second law by saying that the force on a body is proportional to its change of motion or momentum. But by this time he wrote the Principia, he had already developed calculus, which he called the science of fluxions. But in the Principia he made no explicit use of it, perhaps because he believed geometrical arguments in the tradition of Euclid to more rigorous. Whereas consequently the Principia does not express the acceleration as the second derivative of position, and so it does not give the second law as F equals to ma. This form of second law was written for the special case of constant force, at least as early as 1616 by Jacob Hermann Leonhard Euler would imply it as a basic premiere in the 1700 Portage. Euler pioneered the study of rigid bodies and established the basic theory of fluid dynamics. Pierre Simon Laplace 5 volume Traité de mécanique céleste 1798 to 1725 forsook geometry and developed mechanics purely through algebraic expressions while resolving questions that the Principia had left open, like a full theory of the tides. The concept of energy became a key part of Newtonian mechanics in the post-Newton period. Huygens' solution to the collision of hard squares showed that in that case not only is momentum conserved but kinetic energy is as well, or rather a quantity that in retrospect we can identify as one half the total kinetic energy. The question of what is conserved due to all other processes like inelastic collisions and motion slowed by friction was not resolved until the 19th century. Debates on this topic overlapped with philosophical disputes between the metaphysical views of Newton and Leibniz, and variants of the term force were sometimes used to denote that we would call types of energy. For example, in 1742, Emile du Châtelet that wrote dead force consists of a simple tendency to motion, such is that of a spring relax, ready to relax. Living force is that which a body has when it is in actual motion. In modern terminology, dead force and living force correspond to potential energy and kinetic energy respectively. Conservation of energy was not established as a universal principle until it was understood that the energy of mechanical work can be dissipated into heat. With the concept of energy given a solid grounding, Newton's law could be could then be derived within the formulations of classical mechanics that put energy first, as in the Lagrangian and Hamiltonian formulations described above. Modern representations of Newton's law use the mathematics of vectors, a topic that was not developed until the late 19th and early 20th centuries. Vector algebra, pioneered by Joshua Willard Gibbs and Oliver Heaviside, stemmed from and largely supplanted the early system of quaternions invented by William Rowan Hamilton. So also, history of classical mechanics, a list of eponymous law, list of equations of classical mechanics, list of scientific laws named after people, list of textbooks on classical mechanics and quantum mechanics. Reference below. Notes. See, for example, Jane David Tom Lawrence Particle is defined to be an object of insignificant size, example, an electron, a tennis ball, or a planet. Obviously, the validity of this statement depends on the context. Negative acceleration include both slowing down when the current velocity is positive and speeding up when the current velocity is negative. For this and other points that students have often found if see McDormand et al. The study of mechanics is complicated by the fact that the household words like energy are used with a technical meaning. Moreover, words which are synonyms in everyday speech are not so in physics. For is not the same as power or pressure, for example, and mass has a different meaning than weight. For this discussions, for example, Resnick, Schwartz, et al., or Jose and Layton themselves believed that absolute space and time existed, but that the only measures of space and time accessible to experiment are relative. One textbook observes that a block sliding down an inclined plane is what some cynics view as the dullest problem in all of physics. Another argues nobody will ever know how many friends ever to learn the secrets of the universe found themselves studying inclined planes in college student and decided to switch to some more interesting profession. See, for example, the discussion Joseph Salatin, Rothschild et al., as well as Feynman, Neston, and Sands argue that the second law is incomplete without a specification of force by another law like the law of gravity. Kepler and Kepler and Colin Kolenko argue that the second law is incomplete without the third law. An observer who sees one body accelerate without a matching acceleration of some other body to compress it would conclude not that a force is acting but that they are not an inertial observer. Landau and Lifts bypass the equation by starting with the Lagrangian formalism rather than Newtonian. See, for example, Apollo 8 flight and day 5, the green team www.history.nasa.gov 525 2022 checking and United 95 men on the voyages of Apollo astronauts hiking KB 27 63 XB 987 0 67 81446 Thornton Stephen T. Mary Jerry B. 2004 Classical Dynamics of Particles and Systems 5th edition Brooke Colley Newton Isaac Chitenden and W. Mote Andrew Hill Theodore Weston 1946 Mathematics Square The Mathematical Principles of Natural Philosophy University of California Library 10 FD Jane Samia 1919 Techniques of Classical Mechanics from Lagrangian to Autonomous Mechanics Institute of Physics Tom Davies January 2015 Classical Dynamics University of Cambridge Part 2nd Mathematical 3 course University of Cambridge Type 12 February 2022 Gitch Hallett Deborah McConnell, William G. Gleason, Andrew M. International Calculus, Single Numeric Variable, 6th edition, Hoboken, N. J. Wiley, Thompson, Sylvanus P. Gardner, Martin, Calculus, E. McDonald, Lillian C. Rosen, Twist, Mark L. Van G. Mile S. June 1982, student difficulties in connecting graphs and physics. Examples from Kinematics, American Journal of Physics. Chakravarti did further reading. Chakravarti dipped Don Maski repeated Tomasic Michele Flavel Voletic Glide and Cascade Mechanics with open force where Travis 17 January Brighton Thompson W. Jet PG 1867 242 Newton's law of motion treatise natural philosophy. धन्यवाद. Thank you so much. धन्यवाद. Thank you.